firstly I'm starting with the definition of binary operation. If you have studied in class 12th also. What do you understand by a binary operation?
Binary operation is a composition if we have that belong to the if the elements that belong to the some set, and if some relationship also belong to that set, then we call it as binary operation.
If A is a set, a binary operation which I am denoting by this symbol, binary operation on the set A, say star, is a function that maps each ordered pair of elements of A to an element of A. Here I am saying that it is a function that map each ordered pair of elements of A. Means it will be a Cartesian product A cross A to an element of A. That is, star is a mapping from A cross A to A. This Cartesian product will have elements like ordered pair A comma B such that A comma B belongs to A. And moreover, we will be interested in only non-empty sets. So star is a mapping from A cross A to A such that it maps every element A comma B belongs to A cross A to a unique element. Means star A comma B belongs to A. This property is called closure property. Now can you tell me the difference between binary operation and closure property? Basically, binary operation is a function that satisfies closure property. Binary operation is a function that satisfies closure property. Now let us discuss some examples. First, set of natural numbers. I am defining the binary operation as, means I am defining the operation as n cross n to n, means an ordered pair is mapped to A plus B. This belongs to A plus B will belong to natural number. Na? If I am taking two natural numbers, its ordered pair, then if I add these two natural numbers, then they will belong to natural number only. Means plus is a binary operation on natural numbers. Second example, again I am taking set of natural numbers only. n cross n to n means I am taking two natural numbers, ordered pair of natural numbers, a minus b. Is this belong to natural numbers? Means I am asking, is minus a binary operation on natural numbers?
No.
Any example?
1 minus 2.
Hmm.
That will be minus 1. So it is not a natural number.
Yes. This means that minus is not a binary operation on natural numbers. Next, some important notations. Set of natural numbers, which are also known as counting numbers, 1, 2, 3 and so on. Z, set of integers. Integers are basically union of negative numbers, 0 and positive numbers. Set of rational numbers. P by Q. P belongs to integers and Q belongs to natural numbers. Set of irrational numbers. Root 2, root 3, pi, e, root 2 plus root 3 and so on. Real numbers. Real numbers is basically union of rational numbers and irrational numbers. Set of complex numbers. A plus iota b such that a comma b belongs to real numbers and iota is known as root minus 1. Next, z iota. This is set of Gaussian integers. Z iota. This is a plus iota b and here a and b belongs to integers. And this z iota is read as z adjoint iota. Next, definition of group. Can you tell me the definition of group?
Yes, a group is a binary operation that satisfy commutative property, associative property, नोट कम्यूटेटिव नहीं वो तो कम्यूटेटिव होगा तो बेलियन ग्रुप हो जाएगा एसोसिएटिव प्रॉपर्टी एंड एडिटिव आइडेंटिटी एडिटिव इनवर्स and if it satisfy commutative property then it is a Bayesian group.
Yes, so let G be a non-empty set G together with an operation is said to be a group if it satisfies the following properties. Now the properties which I am telling, try to remember them in a sequence, otherwise आगे पीछे कर दोगे तो फिर गड़बड़ हो जाएगी. First property is closure property. For all a comma b belongs to G, A operated with B means this operation can be anything. It can be addition, it can be multiplication, any operation which will be defined. This belongs to G. So this property tells us that the operation on G is a binary operation. Now second property, associative property. For all a comma b comma c belongs to G, I am taking three elements from this group. A composed with B composed with C. This is equal to A composition B composition C. एक सेकेंड रुकना है, कॉल आ रहा है. So associative property means that for all A, B, C belongs to G, if A is composed with B and then B is composed with C, means I am composing A and B together, then I am composing it with C. And if I am composing B and C, then I am composing it with A. This is same in associative property. Third, identity element. There exists A belongs to G such that A composition E is equals to E composition A. This is equal to A. For all A belongs to G means एक ऐसा नंबर जिससे मैं A को मल्टीप्लाई करूँ तो मुझे वो सेम नंबर वापस से मिल जाए. That is known as identity. Fourth, inverse. For each A belongs to G, there exists B belongs to G such that A composed with B is equals to B composed with A, and this is equal to identity. And here this B is the inverse of A. Now in a set, if any element does not have inverse, then that set will not be a group. Now if I give you the operation as addition, and if the operation is multiplication, Can you tell me what will be the inverse in this case? If I am having any element A belongs to G, then in case of addition,
addition on the natural number, सेट क्या होगा जी के लिए?
integers.
तो माइनस से हो जाएगा ना इनवर्स.
Yes, a plus minus a is equals to minus a plus a. And what is the identity in case of integers?
आइडेंटिटी यहाँ पे एग्जिस्ट नहीं करेगी. यहाँ पे आइडेंटिटी एलिमेंट ही एग्जिस्ट करेगा ना. इन सॉरी, हाँ जीरो
होगा ना.
जीरो आ रहा है ना, सॉरी, हाँ जीरो आ गया. ठीक है.
अब ऑपरेशन
मैं सॉरी उसमें प्रोडक्ट में चली गई थी इनवर्स में. हाँ ठीक है.
यहाँ पे मुझे सेट इंटीजर्स की जगह रैशनल्स करना पड़ेगा, अदरवाइज इनवर्स विल नॉट एग्जिस्ट. So in this case it will be a into a inverse. Yes. And identity in case of rationals for multiplication is 1. Yes. Now let us see some examples of group. First, integers, rationals, real numbers, complex numbers under addition forms a group. Now if I am saying that this is under addition, this means that I am talking about usual addition, because we will also study matrix addition, polynomial addition, addition modulo n. So this is usual addition. So this one I am verifying. Z under addition forms a group. So what is the first property? Closure.
Just a minute. Usual addition means, एक बार दोबारा बताना.
Usual addition means simple addition. क्योंकि हम
और अगर एडिशन, हाँ एडिशन मॉडल लेते हैं तो नॉर्मल एडिशन.
हाँ, जैसे ये एडिशन मॉडलो एन, ये वाला सिंबल होता था ना. तो ये नॉर्मल एडिशन है.
ठीक.
So for closure, a comma b, for all a comma b belongs to integers, a plus b belongs to integers. Associativity. For all a, b, c belongs to integers, a plus b plus c, this is equal to a plus b plus c. Identity. Zero belongs to integers. अब रीज़न क्लियर हुआ कि हम सेट को नॉन एम्प्टी क्यों लेते हैं, क्योंकि ग्रुप होने के लिए उसके पास आइडेंटिटी होनी ज़रूरी है. आइडेंटिटी होने के लिए उसको नॉन एम्प्टी होना पड़ेगा. A plus 0 is equals to 0 plus a. This is equal to a for all a belongs to integers. Inverse. For a belongs to integers, there exists minus a belongs to integers such that a plus minus a is equals to minus a plus a. This is equal to 0. Next, integers under multiplication is not a group. Let us see why it is not a group. First property, closure, it will be satisfied. A comma b belongs to integers, then a into b, this belongs to integers. Associativity will also be satisfied. ab into c is equals to a into b into c. Third, identity. Identity element will be 1. Fourth, problem will be in this inverse. Inverse of 0, 2, 3 will not be there. If 2 belongs to integers, then 2 into some number should give me identity. So there is no inverse of this element. Similarly, 0 का भी नहीं मिलेगा inverse. This means that 2 inverse does not belongs to integers, because this can be 1 by 2, but 1 by 2 does not belongs to integers. So inverse element is not there, so it is not a group. Now if I want to make this a group, what I can do, I can remove all those elements which do not have inverse. So I will be left with, if I denote this as z dash, then I will be getting only 1 and minus 1, because in integers only the inverse of these two elements will exist. 1 into some element should give me 1, it will be 1 only. Minus 1 into some element should be 1, it will be minus 1 only. So these are self-inverse elements. Then this is a group under multiplication. Is this clear?
Yes.
Next, third example. A 2 cross 2 matrix whose entries are real numbers A, B, C, D, such that A, B, C, D, these are real numbers. This is a group under matrix addition. Let us verify this also. Now first property, for closure, A comma B belongs to M2R, then A plus B will also belong to M2R. So closure property is satisfied. Second is associative property. A plus B plus C. This is same as A plus B plus C. Can you tell me what will be the identity element for this?
0, 0, 0 matrix.
Yes, 0 matrix. A plus 0 is equals to 0 plus A. This is equal to A. And what will be the inverse?
That is minus A minus B minus C minus D.
Yes, A, B, C, D, minus A minus B minus C minus D. This is equal to 0. This means that A plus minus A is equals to minus A plus A. This is equal to 0. So this is a group. Similarly, MNR, MNQ, MNZ, MNC are groups under addition. Under matrix addition. Now let us talk about whether M2R under matrix multiplication forms a group. First, closure property. A comma B belongs to M2R. Then product of these two matrices will again belong to M2R. What about associativity?
Hold.
Yes, matrix multiplication is associative. What about identity element?
Identity matrix.
Yes. 1 0 0 1. This belongs to M2R, means A into identity is equals to identity into A. This is equal to A for all A belongs to M2R. Now what about inverse? If A belongs to M2R,
But in case of inverse, we have to first take it as non-singular.
A inverse formula is adjoint of A divided by determinant of A. And if determinant of A is 0, then inverse will not exist.
Yes.
Because in this set I have null matrix also in this set. So this is not a group. Therefore, M2R under multiplication does not form a group. Now can you tell me how I can make this set as a group under multiplication by removing some elements?
We can make it non-singular. Then
Yes.
it can be grouped.
So I am calling this set as H. If A belongs to M2R, determinant of A is non-zero, then this is a group under multiplication. Because all the properties will be satisfied, only problem was in this inverse, it will be also satisfied now. Next example, Q plus. Q plus is the set of positive rational numbers under usual multiplication is a group. One belongs to Q plus. This is the identity. For A belongs to Q plus, 1 upon A belongs to Q plus is the inverse. Let me write the definition of abelian and non-abelian group also, so that we can discuss in every example. Abelian group. So by all those 4 conditions, we will have one extra condition for abelian group, that is commutative property. A group G is said to be an abelian group if A into B is equals to B into A for all A comma B belongs to G. This is commutative property. Next, non-abelian group. A group G is said to be a non-abelian group if there exists at least one pair of elements A comma B belongs to G such that commutative property is not satisfied. Now, in these examples only, all these examples are abelian also or not? Under usual addition, they are abelian, na? Commutative property will be satisfied.
Yes, in the case of integers under addition. Yes.
For rationals also, for real numbers also, for complex numbers also.
Yes.
This simply means that A plus B is equals to B plus A for all AB belongs to integers. And this M2R, this is also abelian. A plus B is equals to B plus A for all A comma B belongs to M2R. Is this Q plus abelian? Set of positive rational numbers under usual
ma'am.
multiplication.
Abelian.
Yes, Q plus is an abelian group. Now is the set of rationals under usual multiplication a group? It is not a group because closure property will be satisfied, associative property will be satisfied. For this, identity element will be 1. What about inverse? Is inverse of every element will exist?
0 का नहीं exist करेगा ना?
Yes. 0 belongs to rationals, has no multiplicative inverse. The set Zn, this is 0, 1, 2, so on till n minus 1, is a group under addition modulo n. So here also closure property will be easily satisfied, associative property will be satisfied, identity element will be 0. 0 belongs to Zn is the identity element. Inverse will be same. If A is any element of this Zn, then minus A will be the inverse. So it is a group. Now is it an abelian group? It is an abelian group, na? As commutative property will also be satisfied. I can also say that for J belongs to Zn, n minus J, this will be the inverse of J. sorry, this will not be the inverse, this will be when it is usual addition, but it is addition modulo n. So for this, inverse will be for j belongs to Zn, n minus j is the inverse of j. For example, if I take simple example z2, then z2 is 0, 1. If I take any element from this, 1 belongs to z2, then n is 2. So 2 minus 1. 1 is the inverse of 1. And if 0 belongs to z2, then 2 minus 0. This is 2, and modulo 2 will be 0. So this is the inverse of 0. This means that in z2, 0 and 1 are self-inverse elements. Next, R star. R star is the set of non-zero rational numbers. Sorry, the set of non-zero real numbers under usual multiplication is a group. Closure property will be satisfied, associative property will be satisfied. What will be the identity element here?
One.
Yes, 1 belongs to R star is the identity. And what will be the inverse?
1 upon the element is inverse, reciprocal.
Yes. For A belongs to R star, 1 upon A belongs to R star is the inverse of A. Commutative property will also be satisfied. So R star is an abelian group. In general, the set of 2 cross 2 matrices with real entries under matrix multiplication is not a group, as the inverse of every matrix does not exist in general. This we have already discussed. Thus, for A belongs to M2R such that determinant of A is non-zero, then A inverse exists. Now define. The set which I have defined was general linear group, GL2R. A belongs to M2R such that determinant of A is not equal to 0. This is general linear group. It contains 2 cross 2 matrix whose entries are real numbers and whose determinant is non-zero. Now we will verify that this is a group under usual matrix multiplication. GL2R under usual matrix multiplication is a group. So first property, closure property. Let A comma B belongs to GL2R. Determinant of AB. Now if A and B belongs to GL2R means determinant of A is non-zero, determinant of B is non-zero. And if I want to prove that AB belongs to GL2R, this means that I need to show that determinant of AB is non-zero. Now the property of determinant of AB is determinant of A into determinant of B. Determinant of A is non-zero, determinant of B is non-zero, so this is non-zero. So AB belongs to GL2R. Second is associative property. Matrix multiplication is associative. A into B, then multiplied with C, or if I multiply B and C and then I will multiply with A. So associative property holds. Identity 1001, this belongs to GL2R. This is the identity element. Fourth, inverse. For each A belongs to GL2R, A inverse is adjoint of A divided by determinant of A. So determinant of A inverse. This is determinant of A whole inverse. And determinant of A is non-zero because A belongs to GL2R. This implies A inverse belongs to GL2R. Thus, from first to fourth properties, GL2R is a group called the general linear group. From real entries. Next, Zn 0, 1, 2, so on till n minus 1. This is not a group under multiplication modulo n. Reason is, for J belongs to Zn, J inverse exists if and only if GCD of J comma n is 1. So by this I am defining a new group which is UN. X belongs to Zn such that GCD of x comma n is equals to 1. Set of all positive integers less than n and relatively prime to n. This is the condition for prime now. If GCD of x and n is 1, forms a group under multiplication modulo n. This is also known as group of units. And it is a very important finite abelian group. Next is Cayley table. It is also known as multiplication table. Do you remember Cayley's table?
Okay.
नहीं याद?
नहीं याद.
कोई नहीं, अभी एग्जाम्पल करेंगे फिर क्लियर हो जाएगा. This is useful for finite groups. अभी तक जो समझाया क्लियर है?
हाँ, वो क्लियर है.
ठीक है. With less number of elements. If G is a finite group, with operation, the Cayley table of G is a table with rows and columns labeled by elements of G. The entry in the row is labeled by A belongs to G, and the column entry is labeled by B belongs to G. Then this is the element A into B. For example, construct the multiplication table or Cayley table of U5. So U5 means, by this definition, X belongs to Z5 such that GCD of X comma N, and here N is 5, it is 1. So can you tell me what will be the elements in this? One, two, three, four. All these elements will have GCD 1 with 5.
Yes.
Now, and here the operation will be multiplication modulo n, means like this. And in all the rows and columns I am going to write the elements of this U5. So 1, 2, 3, 4, 1, 2, 3, 4. So multiply this one with this one. Answer will be 1 only. 1 into 2, 2. 1 into 3, 3. 1 into 4, 4. Similarly here also 2 into 1, 2. 3 into 1, 3. 4 into 1, 4. Now 2 into 2, 4. 2 into 3, 6. And multiplication modulo 5. It will be
1.
Yes. 2 into 4, 8. Multiplication modulo 5.
3.
Basically, yes. Basically, I am dividing 5. I am dividing 8 with 5. And after that, whatever remainder is left, this is my answer. So 3 into 2, 6. 1. 3 into 3, 9. 4. 3 into 4, 12. 2. 4 into 2, 8. 3. Again 12. 16. 1. So this is how we will create Cayley's table. Next, properties of Cayley's table. First, every row and every column of the table should contain each element exactly once. You can clearly observe that each row and each column has a particular element only one time. Otherwise, the operation is not a binary operation. Means repetition of any element in any row or any column is not allowed. In which cancellation law holds. I will discuss this cancellation law also after some properties of Cayley's table. For example, let us consider the set Z4. Z4 contains the element 0, 1, 2, 3 under multiplication modulo 4. Zero, 1, 2, 3. Zero, 1, 2, 3. So first row will be 0, 0, 0. So clearly it is violating this property because each row and every column of the table should contain each element exactly once. And rest of the elements will be 0, 1, 2, 3, 0, 2, 0, 2, 0, 3, 2, 1. In this 0 and 2 appears twice. Thus multiplication modulo 4 is not a binary operation in which cancellation law holds. Now, what do you understand by cancellation law? It is basically if G is a group for ABC belongs to G such that AB equal to AC, then this implies B equal to C. This is left cancellation law. BA equal to CA. This implies B equal to C. This is right cancellation law. So here what will happen? 2 into 0. 2 into 0 is equal to 2 into 2. Because in both this I am getting 0. So by following this cancellation law, it should be that 2 is equals to 0, which is absurd. This is not possible. Second property of Cayley's table. There should not be any entry except the entries in the leading row or the leading column otherwise the operation is not closed. For example, under usual addition, simply usual addition, is not a binary operation on the set. Z4 equal to 0, 1, 2, 3, because this is plus 0, 1, 2, 3, 0, 1, 2, 3. Zero, 1, 2, 3, 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6. Clearly, there are elements which does not belongs to Z4. 4, 5, 6 does not belongs to Z4. There are elements except the entries in the leading row or the leading column This means that addition is not a binary operation on Z4. Next, third property, the identity element of the group should be symmetrically distributed about the main diagonal. Otherwise, one or more elements do not have inverse. Fourth property, if the row headed by the element, say aj, coincides with the leading row, and the column headed by aj coincides with the leading column, then aj is the identity element. For example, in this U5, this first row and first column coincides with this one. So here 1 is the identity element of U5. For example, if this is the 1, then 1 into which element should be 1? 1 into 1 only. 2 into 1 will be 2. 3 into 1 will be 3. 4 into 1 will be 4. Fifth, if the entries in the table is symmetric with respect to the main diagonal, then the group is abelian. Now we will discuss some elementary properties of groups. First property is uniqueness of identity. So if G is a group, then the identity element is unique. Then the identity element E of G is unique. Let us discuss its small proof also. Let G be a group. Let E and E dash be the identity elements, and I want that identity is unique. So I need to show that E equal to E dash. Now, by the definition of identity element, A E is equals to EA is equals to A for all A belongs to G. A E dash is equals to E dash A equal to A for all A belongs to G. And in particular, if I take E into E dash is equals to, if I take A as E, then E into E dash is equals to E into E dash is equals to E. Here also E dash into E. this is equal to E into E dash, this is equal to E. So this implies that E is equals to E dash. So the identity is unique. Next, second, cancellation property. If G is a group for A, B, C belongs to G such that AB equal to AC implies B equal to C, this is left cancellation. BA equal to C, CA implies B equal to C, this is right cancellation. Small proof this. For this also, let G be a group ABC belongs to G such that AB equal to AC. Now as A belongs to G, so inverse will exist. A inverse belongs to G. Simply pre-multiplying by A inverse to equation 1. So A inverse AB is equals to A inverse AC. This implies A inverse A into B is equals to A inverse A into C by associative property, because G is given to be a group. This implies E into B is equals to E into C, B is equals to C. Next is uniqueness of inverses. For each element A, in a group G, A inverse is unique. Proof. Let G be a group and A belongs to G. Here also I am supposing that there are two inverses for a single element. Let if possible B, C belongs to G be two inverses of A. So this implies AB is equals to BA is equals to E. AC is equals to CA is equals to E, because I have supposed that B is an inverse of A and C is also an inverse of A. So this implies AB is equals to AC. This implies B is equals to C because by left cancellation law. So inverses are unique. Fourth property, sock shoe property. Let G be a group for A, B belongs to G AB inverse is equals to B inverse A inverse. Proof. G is a group, A, B belongs to G, so inverse will also exist. A inverse, B inverse belongs to G. Now by closure property, AB belongs to G. AB into AB inverse. This is equal to E. So AB inverse is equals to E. Now pre-multiplying by A inverse, I will get A inverse AB inverse. This implies A inverse AB inverse is equals to A inverse because by associativity. This implies E into B, AB inverse is equals to A inverse. This implies B into AB inverse is equals to A inverse. Now pre-multiplying by B inverse. B inverse B AB B inverse B AB inverse. Again applying associative property, B inverse B AB inverse, because by associativity. This implies E into AB inverse equal to B inverse A inverse. This implies AB inverse is equals to B inverse A inverse. This is the required property. Next, note first, if the group is abelian, then B inverse is equals to A inverse B inverse. So here we can say that this will become AB inverse is equals to A inverse B inverse. This will be valid only when group is abelian. Second property, for A1 A2 so on till AN belongs to G, A1 A2 so on till AN inverse is equals to AN inverse AN minus 1 inverse so on till A1 inverse. Third, for A belongs to G, A inverse is A. Means if I see inverse of A and again I take its inverse, then I will get the same element A. Next property, law of exponents for abelian group. Let G be an abelian group for any A comma B belongs to G, AB to the power n. This is equal to A to the power n, B to the power n. For all n belongs to natural numbers. Sixth, in a group G, if A square is equals to E for all A belongs to G, then G is abelian. Means if any group G, square of any element is identity element, then that group G is abelian. Next, order of a group. the number of elements in a group G is called the order of the group denoted by OG or like this. For example, if I have Z9, then it will have 0, 1, 2, so on till 8. So order of Z9 will be 9. Z is an infinite group under addition. Next is order of an element. Let G be a group and A belongs to G. If there exists smallest positive integer n such that a to the power n, this is equal to e, then n belongs to natural numbers, is said to be the order of A. Order of
A.
Order of A. And it is denoted by OA or like this. If there does not exist any positive integer such that a to the power n is equals to e, then we say order of A is infinite. Order of identity element will be 1. Identity is the only element of order 1. Second thing, if a group is finite, then order of every element is finite. But converse need not be true. If order of every element is finite, then it is not necessary that a group is finite, that a group is of finite order. For example, if I take power set of natural numbers with symmetric difference operation. Another example, Z2 cross Z2 cross Z2 and so on. We know that every element in this Z2 is of finite order, but this group G is not of finite order. ठीक है, आज यहीं तक रखते हैं. इसके बाद नेक्स्ट क्लास से सब ग्रुप्स पढ़ेंगे.